Smith from the CSIRO from Perth, Australia. I have a list what to read given to me. He's an early career researcher. This is quite modest. I would say it's a rising star. Specializing in magmatic ore deposits and with a lot of experience in the study of the layered intrusions and nickel sulfides, PG reef, granite-related wolfram and tin occurrences. He investigated critical metal occurrences in many places around the world, in Canada, in South Africa, in Greenland. And he already contributed to several review papers on the layered intrusions. Now he is working, as I said, in CSIRO. His research mostly on advancing the understanding of magmatic ore forming processes to identify prospectivity indicators and translate them into practical vectoring tools. His visit to South Africa partly sponsored by Bushveld, and we are looking at kind of opportunities to maybe to have some joint research projects between CSIRO and Wits University. And tomorrow we're already leaving to the Bushveld Complex for the week, and then to the workshop, Bushveld workshop, to get familiar with this. And of course, William already been here for the Platinum Symposium a long time ago. Was it?
Yes,
2018. Yeah, something. So it's not totally new for South Africa. So you knew something, but still now they will be already.
Yeah.
Okay, thank you very much.
All right, cheers, Rick. All right, okay, I'll stay close to the mic. Yeah, thank you, Royce. And it is a it's a real honor to be invited here to South Africa to do some field work. So I feel quite brave talking about the Bushveld to all the South Africans here. But so this is going to be mostly on work that was published earlier this year in the Journal of Petrology. Going to talk a bit about some observations made in that and also some forward-looking statements for research that's going to be ongoing. And Royce and I are going to be discussing lots of things in the field in the next few days. So I acknowledge all the people that have sort of collaborated and given me comments on this study, including the reviewers, some of which are in this room as well, that gave me a lot to think about. And there is certainly a lot to think about in the Bushveld Complex. So quick summary, Bushveld Complex is the largest known layered intrusion, host of significant PG and chromium resources, and it is also home to the Merensky Reef. So this is a simplified map of the Western Lobe. And the Merensky Reef sits in the upper critical zone of the stratigraphy, which is in this sort of purple color. And the sample I'm going to be talking about today, or the observations, were largely made from the samples taken from the Rustenburg Platinum Mine located here where this star is. So here is an image of this sample, and we did quite a detailed petrographic study of this sample in 2021. In terms of facies of Merensky Reef, there is some variability along strike. The footwall can change from anorthosites, norites, troxylites in places as well. But what we're going to be talking about today is mostly this normal narrow reef facies that is typified at the Rustenburg Platinum Mine. And what this has is we have a footwall norite and a anorthosite that is overlain by a relatively coarse-grained pyroxenite that is bracketed by chromatites on either side. And then that is overlain by a relatively finer-grained hanging wall pyroxenite there. So when I refer to reef in this case, we refer to the extent of the sulfide mineralization, which extends from sort of the top of the footwall norite up to the hanging wall pyroxenite. So this is where the sort of mineralized package of rocks is. So there's many different models proposed for this horizon. Some really rather quite different from each other as well, ranging from magmatic to hydromagmatic processes. I'm not going to really go into each of the different models today. There are many, but I will propose sort of what we proposed for the formation of the package of rocks we were looking. And the model we ultimately proposed takes elements from lots of these different models as well. There's many observations from this horizon going back to way before I was born. And sort of synthesizing all those observations was a real challenge. But yeah, lots of little observations that maybe seem not that important could actually be quite insightful for how this horizon formed. So I want to, hopefully I captured a lot of observations from people, but there's still much to learn. So the layout of this talk is I'm sort of going to go through what we thought, the evidence of why we thought it in sort of a staged fashion. So the first thing that we think happens for the Merensky Reef is that we have sort of a standard magma chamber we have cumulates forming at the base. Those cumulates likely get more leucocratic with height, density of the mineral settling. We have sort of a weak lamination within the cumulates there, which we ascribe to settling. And then ultimately, we have some sort of chaotic event that changes things. We have replenishments of melts, multiple perhaps, that erode the footwall cumulates and create sort of a relatively irregular topology. And the intensity of that is very likely to be very variable along strike, but I can't really speak for things going across the Bushveld until I've probably seen a lot more of it. But this is what I think happens in stage one. So looking at the cumulates in the footwall norite, why do we think they're settling in a relatively calm melt? So what we have is we have cumulus plagiate clays, cumulus orthoproxene, and the orthoproxene has these poikilotic overgrowths there on the side. The fabrics of the cumulus plagiate clays are sort of weakly foliated, and this is sort of a hallmark of tabular phases settling within a calm melt. That's from research of sort of Holness, Cheadle and Gee, and other people that are far greater experts in EBSD than me. So this is from layered intrusions, mid-ocean ridges as well. They consider this a hallmark of gravitational settling. And there was no way I could really argue with that. So we decided that this has to be sort of a settling horizon, calm package of rocks growing on the floor. Then we get this quite chaotic event that seems to cut things up, erode things. And this is evidenced largely from field observations, lots of work of photos of rice have shown this, but also many studies before have shown these cross-cutting relationships into the footwall and how this sort of Merensky horizon undercuts into the floor rocks as well. This is taken, I think, as quite compelling evidence that we have sort of erosion of a cumulate pile, and we have this sort of unconformable horizon that the Merensky forms on. It isn't just field observations that support that, though. This horizon comes with sort of chemical breaks, isotopic breaks that seem to be consistent with some sort of replenishment event or some sort of event that changes what's currently happening in the chamber. Minerals within this horizon can be in isotopic disequilibria as well. So clearly there's some hybridization or something going on that means the system isn't necessarily in equilibrium. So taking these observations, chemical, isotopic, field into consideration, we consider this to be an unconformable eroded horizon that the Merensky was deposited on. So the second stage is, I think there's a lot of overlapping processes that happen, some probably related to one another, but maybe some circumstantial. But clearly a lot happens to form one of the world's premier ore deposits. So here's what I think, how we go. So I think at some point, replenishment amounts perhaps wane, and we have sort of supercooling or crystallization of skeletal chromites on the base there. I think we partially melt the leucocratic footwall to make an anorthosite restite. And I think that melts liberated from that footwall react with the skeletal chromites and other things to form the chromatite we see at the lower chromatite. Yeah, that's everything I'll say. So why do we think the anorthosite is a restite of melting? So the image to the right there is an element map at the transition between a leuconorite and a anorthosite. And I'll sort of rattle through a few lines of evidence there that I think make this a sort of anorthosite restite. We have a peak in late stage phases at the transition zone. We have a higher modal abundance of quartz, mica, intercumulus chloroperoxene there at the transition zone. We have fine-grained chromite distributed actually in a greater modal proportion right at the top of that footwall norite, sort of in association with the poikilotic rims of the orthoproxene. And that sort of abruptly stops at the transition with the anorthosite. But you'll see, so these orange circles all represent fine-grained chromite crystals. And you'll see that actually they do persist within these sulfide silicate networks that traverse the anorthosite horizon here. So we see chromite. Again, the sulfides, these sinuous sulfide silicate channels, they traverse the anorthosite and they generally don't go much further down than the top of the footwall norite. We consider that as evidence that sulfide is going sort of percolating downward and stalling at the point in which the melt reaction has not quite reached. So sulfides exploiting the porosity generated in the anorthosite restite. Looking at the intercumulus clinopyroxenes at that horizon, we see a lot of features that have been ascribed to sort of remolten rock. So taking observations from Marinus Holnis's work from remolten granulites, we see several features that seemingly consistent with the remelting of rock. So we see sort of films growing of clinopyroxene around cumulus silicates, and we also see these bulbous terminations in the intercumulus clinopyroxene as well. And here's an image of a remolten sort of melt pocket there from some of Marinus Holnis's work. So we consider this to be another line of circumstantial evidence that this was a partially remolten horizon. So moving on from petrography into chemistry, the thickness of the poikilotic rims sort of increases as we get closer to the anorthoside at the expense of the cores of the orthoproxene crystals. And those relatively more poikilotic crystals have lower magnesium numbers than the orthoproxene somewhat below, despite the chromium and titanium concentrations being exactly the same. And what we've managed to model this as is a result of trap liquid shift at this horizon, which is somewhat in keeping with the fact that we see an increased proportion of quartz mica evolved phases within this horizon as well. So we can generally model these shifts quite effectively as 5 to 10% trap liquid shift, which I think is kind of in keeping with the amount that other studies have estimated for this horizon as well. So evidence that there was sort of melt at this horizon, and there's a little bit of porosity in the anorthoside above it. So change in magmatic fabric. So now we're going upward through the anorthosite towards the lower chromatite. Yes, we have fabrics that were once consistent with gravitational settling alone, in my opinion. But the fabric of the plagioclase, as we get closer to the lower chromatite, increases to a degree that is now no longer explainable only by gravitational settling. The fabric is strengthened, and another mechanism is needed to explain why the fabric is as strong as it is. And I'll circle back to that later on in the presentation. So the chromatites are probably one of the more difficult things to wrap my head around. I think there's a lot of evidence for out of equilibrium growth of the chromatites, particularly in the lower chromatite, but there's a lot of features here that need to be explained, right? There's these really sharp lower contacts, we have these undulose upper contacts, and we have this bimodal population of chromatite that needs to be explained. So what I mean by bimodal is we have this population of sort of blocky, unassuming, kind of relatively boring crystals, I guess. And then we have these larger, irregular, lots of inclusions, strongly misoriented chromite crystals as well. And they don't really care about what the host crystal is, the relative point in the stratigraphy of the chromite. They're sort of distributed heterogeneously throughout this horizon. So that needs to be explained in any model. So more support, not just looking at them, but looking at crystal size distributions, particularly from the lower chromatite. Crystal size distributions support this bimodal population. And again, that extends whether it's in an orthoproxene or a plagioclase. There's a bimodal population here that needs to be explained. And several other studies have reported that. That's not from me. Petrographic features within the chromites, looking at these amoeboidal crystals, we can see that from some of Marina Yudovskaya's work and other studies looking at other sort of chromatites within the Bushveld and elsewhere, is that we have a lot of features seemingly consistent with dissolution, reprecipitation. We have sort of etch channels, serrated margins, these sort of fishhook structures that sort of consistent with this process of dissolution, reprecipitation. And we think that sort of is driven by sort of relatively evolved melts liberated from the anorthosite as it's undergoing this reconstitution process. Whether that's right or wrong, it doesn't really matter. But again, it's something that needs to be explained in any model as well. Lots of observations. But another reason we think the chromite is sort of undergoing a phase of quick disequilibrium growth, and this is something that's currently in review at the moment, is that in a lot of these large amoeboidal crystals, we have regions of them that are really inclusion rich. And those inclusions can contain phlogopite, mica, sulfide, lots of evolved phases, PGE rich sulfides as well. And looking to publish this, so I'm not going to say too much about it now, but what we found in the inclusions is that there's strong epitaxy between what's in the inclusions and the chromite itself. Which is compelling evidence that whatever minerals are in the inclusions nucleated directly onto the chromite crystal. So we think we have a skeletal chromite crystal, lots of phases crystallizing within the sort of scaffolds of that skeletal crystal, and then sort of returning to some sort of normal growth. I'm quite excited about that because the implication is that the PGE-rich sulfide inclusions in the chromite, we need to get PGE into them. Yeah, I find that quite interesting. How do we get these PGE-rich sulfide droplets nucleating in situ on the skeletal chromite? But maybe the review is completely been rubbish, I don't know. Anyway, out of equilibrium chromite growth. So not just petrography, but also chemical observations. When we look through the lower chromatite, upwards through, it gets more chrome rich, it gets more iron rich, and it also gets more titanium rich. All the white circles there are rutile, and we actually get a real peak in rutile as we get sort of more upward through the lower chromatite, and it's also throughout the upper chromatite as well. So lots of rutile, lots of titanium. What we ascribe this to is that it's actually related to orthoperoxene and trapped liquid. So as the rock cools, there's a temperature sort of dependent exchange between spinel and orthoperoxene, and that drives this sort of chromium iron rich chromite. And you can see that when we look at the orthoperoxene sort of EPMA transits here, is that they actually get more magnesium and chromium poor when they're in contact with chromium. So we can explain pretty much all the chemical variations in the chromites with some reaction with trapped liquids and re-equilibration with chromite with orthoperoxene during cooling. So I actually don't think there's much to read into there, just re-equilibration. Yeah. So moving into modeling worlds, so we wanted to sort of see if we could generate an anorthosite from melting different types of floor rocks. So I'll just highlight a few of the models we presented here. So we reacted different replenishing melts, B1, mixtures of B1, B2 with different footwalls, leucocratic ones, melanocratic ones, just to see what kinds of things we would get. And we found that, yes, we could produce an anorthosite in certain cases when there was sort of a relatively hot magma like a B1, ideally water rich. The more water in there, the slightly easier it is. But we can generate an anorthosite if it reacts with a relatively small portion of the rock. And actually this anorthosite horizon is centimeter scale, and there's an abrupt transition there with the footwall norite. So we think it's completely feasible to remelt a leucocratic rock, get to its eutectic point, and then it becomes really difficult to melt because then it's just pure plagioclase practically. So we think this replenishment through these models is quite feasible. I think the limitation with these models really is that there's always olivine, and we don't really see olivine. So I think that's one limitation that I haven't quite managed to figure out. We do see quartz throughout this horizon. Maybe olivine simply is unstable, but yeah, the models always like olivine, even if there's a small portion of water. So that's something that I think needs to now be looked at. Interestingly, with the melts, no matter how much water you put into the melt or the footwall or whatever, the first melts, the most fusible portions of the footwall that are liberated and introduced to the lower chromatite, they're always relatively volatile rich. They always have the highest portion of water. It's the easiest thing to introduce out. So we think even if it's not that wet, we can still introduce a relatively increased proportion of volatiles to this sort of nascent chromatite layer. So period of calm, the diagram next actually doesn't look very calm, but I assure you that it is calming down a bit. So we have the lower chromatite forming now, dissolution, reprecipitation, probably some nucleating above now as well. But essentially we have sort of a nascent lower chromatite forming. Ultimately sulfides come in, those sulfides percolate into the relatively porous footwall, orthoperoxene crystals settle and probably embed into the chromatite. And at some point this thing coarsens into that sort of pegmatodal horizon. The coarsening I find is the most ambiguous in my mind. I'm not fully convinced how that works, but it happens and it needs to be explained. Okay. So at the top of the cumulate pile, the plagioclase crystals are quite strongly reversely zoned, much more anomalously reversely zoned than plagioclase from below it. And this is generally what's referred to as a bleach zone. And it's this horizon of relatively coarse-grained, strongly anorthositic plagioclase just beneath the lower chromatite. This needs to be explained because it persists throughout a lot of different intervals within the Bushveld, in the boulder bed, in the pseudo reef, and in other places as well. We always seem to have this sort of relatively calcic plagioclase layer that needs to be explained. So before I go on to that, I'll just highlight, here's this sort of pure anorthosite layer beneath the lower chromatite. But then just below that is this pretty much almost gabbroic horizon. We have huge carnoperoxene oikocrysts that sort of go maybe a couple millimeters away from the lower chromatite there. And I wondered about this a lot, and I didn't see it written about a lot either. So we did some EBSD in chemistry on this oikocryst here, and we found, yes, they are quite large oikocrysts, but they're also really magnesium, and they're also really titanium and really chromium rich. Some of the most chromium rich carnoperoxenes in the Bushveld as well, which I found quite interesting. So I consider these oikocrysts as sort of an analog for the types of melts that were liberated from the anorthosite and being introduced to the chromatite. And the reason they stopped there is because we ultimately cut off chemical communication between the floor rock and the overlying melt. And that's, oh, actually, I'll get onto that. It's quite exciting, I think. So looking at the plagioclase crystals there, we see we have, yes, these reversely zoned, quite anorthositic plagioclase crystals, but they actually grow sort of, I don't want to say grow upwards, that's just inferring, but they sort of integrate upwards into the lower chromatite as sort of these quite large, almost bladed crystals as well. So we've seen this in a couple samples. Other researchers have shared other examples of this to me. So we have these really coarse-grained, somewhat weirdly zoned plagioclase crystals extending up. And those oikocrysts are trapped beneath these crystals. They're trapped beneath these crystals. The zoning isn't simply reversely zoned. So this laser map here is an oikocryst, plagioclase oikocryst. And we can see that the sodium actually changes in concentration relative to the proximity to chromite. I thought this was some diffusion process. We did some laser profiles across the contacts. Doesn't seem to be any real diffusion with the chromite. Chromite doesn't accept sodium at all. So I don't know how to explain that necessarily. I think maybe sodium is being leached by some process. Maybe Ilya Vex's paper, I think, is reasonable. But it's not simply reversely zoned. It's weirdly zoned. Yeah. So somebody shared, when I was discussing this sort of weird oikocryst, somebody shared me these analog experiments from 1980s by Kerr and Tate. And what they were simulating was a sort of a porous footwall and an overlying melt column, and just sort of calling it and just seeing how melt exchange operates between those two phases. And what they found is the first thing that crystallizes is very, very coarse-grained crystals at the interface. And what happens is beneath these very coarse-grained crystals actually stagnated melt that was originally undergoing exchange, and they crystallized almost as oikocrysts. So I consider these very coarse-grained bleach plagioclase crystals to be equivalent to these capping crystals, and the oikocrysts just to be melt that's trapped beneath them that wasn't able to be liberated back into the lower chromatite. I think some of these analog experiments are awesome, and I think we should really do a lot more of them. So I encourage people to look at that if they're interested in this. So then we have the coarsening, and I said I don't think I have a good explanation for this at all. We found sort of chromite rims within the orthoperoxene crystals that some people have ascribed to being the original outline of the orthoperoxene crystals that subsequently coarsened. Oh, I don't know. Definitely coarsened. What we do know is that the undulations in the upper chromatite, in the lower chromatite, in the upper contact, they undulate according to the orthoperoxene crystals that then extend downward as oikocrysts into the upper portion. Looks like crystals settling in and pushing down into the upper chromatite, into this contact to me. Maybe it was in situ, I'm not too sure. I think that probably settled into that and pushed down into it. Because we don't see the same things going upward in the upper chromatite. The upper chromatite actually blankets the orthoperoxene crystals almost perfectly. So the contact between orthoperoxene and the two chromatites are fundamentally different. So they need a different explanation. Okay, moving into the final phase of the story. We've coarsened it by some mechanism. I'm not going to elaborate too much more. But the melt comes in and we have a sort of another event, another erosive event. We erode this in places, and Rice has shown me some quite compelling photos of this in other parts of the Bushveld. So I'm quite convinced that the upper chromatite is now being emplaced by a separate replenishment event. But the reason we don't see the same amoeboidal crystals or the same textures in the upper chromatite is because it's not interacting with the footwall melts anymore. It's already kind of hot at the base, hasn't got this supercooling happening, hasn't got melt exchange happening. So it has a sort of a relatively different sort of post-cumulus history, let's say. So the chromite's deposited, then we get some more sulfide, and then we get some orthoperoxene to start making the hanging wall. So I think the hanging wall has to have come last. And I sort of ascribe this to how sulfide is distributed throughout this horizon. There's a lot of compelling field observations, petrographic work, tomography work done that shows that sulfides spike in the chromatites and just above the chromatites. Experimental evidence seems to suggest that sulfides should love going through chromatites, but that's definitely not what we observe in the rock. Sulfides seem to stagnate above chromatites for whatever reason. So what we take this as evidence for, particularly when we're looking at the hanging wall, is that sulfides are percolating through the hanging wall and they're stalling above the upper chromatite. So I think that's relatively compelling evidence that the hanging wall has to come after the upper chromatite. Okay. There's definitely good evidence for melt exchange. So I saw before that we have sulfides going into the anorthosite. Sulfide has to go into something. So something is obviously being liberated out as sulfide goes down. Has to happen. We see that in the anorthosite, and we also see that here in the upper chromatite. A lot of independent studies have shown that the peak chalcophile metal concentrations are offset vertically by peak incompatible element concentrations, and this has almost been always ascribed to sulfide going down a little bit and trapped silicate melt going up a little bit. I think that's probably the most reasonable thing. This is probably subject to a hell of a lot of sampling bias, though, so probably needs to be validated some other way. But quite, to me, compelling evidence that we've got sort of two-phase melt exchange in these cumulus. Reason. Then we get up into the hanging wall, and I think it marks a complete return to normality. We have sort of normally zoned orthoperoxene crystals, except when they're next to chromite, undergoing this post-cumulus cooling process. And their fabrics return to exactly how we saw plagioclase in the footwall norite. So this is a hallmark again of settling of crystals within a melt. Whatever has happened, it's happened now. And we return back to normality in the hanging wall. So I think there's a lot of processes there that I've rattled through, and I probably missed a few things. It's all in the paper. I tried to cite as much evidence as possible throughout it, but people can challenge that. So I think a lot of those processes accumulate. When we get to the ends, we have some compaction that probably causes 99% of the small localized misorientation we see. There's no evidence for deformation in this horizon at all. We have post-cumulus processes, some trap liquid shift, all these things sort of happen at the post-cumulus stage. But yes, Merensky is formed. So yeah, thank you for that. And I'm looking forward to any questions. Yes.
We have time for questions, please. Go ahead. Will you like me to come?
That's okay. Yes.
Okay, good.
Yes. Oh yes. Sorry. Yes.
I think you explained the formation of the lower chromatite string by increased constitution of
the lower chromatite. Yeah. So we have in situ sort of rapid crystal skeletal crystals, and then we have dissolution reprecipitation of those to make them sort of more regular, more amoeboidal. And in that process, we also get some sort of more blocky crystals settling at the same time.
Okay, so do you think that the dry crystals of the chromium
Yeah, this is a good question. So we did some general mass balance, and it would if the chromium was just supplied by the footwall, we'd have to melt the orthoperoxene from around 30 meters of the footwall. So I think the actual melt coming in is the primary source of the chromium. But as I said, those client peroxene oikocrysts are actually really chromium rich. And there is little chromites throughout the sinuous channels in the footwall. So there's definitely chromium coming up. What role that plays in actually informing the chromium, I'm not too sure. But there's definitely chromium coming from here and from here. Does that answer? Yeah. Go on. Yeah.
The inclusions.
Yes. Yes. Yeah.
There's lots of evidence. Still water.
Yeah.
Often these inclusions are
Yes. Yes.
I think you said that this is malleable being trapped into that frame.
Yeah. Yeah. Yep. So I don't think they're analogs for the parent melt. I think there's a lot of compelling evidence for that. But the epitaxy of the crystals on the chromite was, by people that know EBSD far better than me, said this crystal has to really crystallize on this. There's no other way to explain it. So I think it's probably more evolved because we're getting relatively evolved melts from the foot. I think the skeletal chromite is crystallizing quickly, the scaffoldy crystal, and the most fusible melts just happen to come out at the same time. And they seem to like to wet chromites, and that's why we get the evolved wetter phases of the chromite. I think that makes complete sense.
Thanks, William. Really well illustrated talk on fantastic models. Correct me if I'm wrong, but you're asking incoming presumably superheated melts to do quite a lot of things, right? You're asking to erode the football,
Well, okay, well that's interesting as well, because I think the melt that does the eroding doesn't necessarily have to be the melt that does the crystallizing. I don't know. It's probably very variable along strike as well. It's probably variable with what the footwall is. If it's a footwall that maybe is cooler, easier to melt, maybe it's slightly different interaction between the two.
I guess what I'm wondering is, over the extent of the entire Rustenburg layer,
Yes.
you have to, I don't know how variable this is now,
Yeah.
I'll ask this question, right? I don't know how variable this kind of evidence is naturally throughout the Bushveld, but
Yes.
I just feel like you're asking a lot in terms of
Yeah.
thermodynamics.
Yes.
Yeah, erosion, all the melting of a very difficult rock to melt, right? But yet you just do the Merensky Reef over the entire Rustenburg.
I think any problem with scale is just the problem here, right? Everything is a scale, and that's so hard to explain. I think the fact that it is across the whole thing calls for a chamber-wide phenomenon. So however marvelous it may be, it has to be chamber-wide phenomenon to be able to do what we see.
Yeah. I think it is marvelous, but then the question is,
Yes.
surely if it's, unless it's melt coming from many different sources, all at once, at the same time, the entire surface area, you would lose some of the thermal energy with natural flow, right? Like, so
Yeah.
versus the feed gets very prominent, and far away, you might be cool.
Yeah.
It's lost some energy.
Yeah. No. Yeah. I think, because I originally obviously wanted things to be entrained, happy days, we've got PG sulfides, great. But then if it's full of crystals, we can't really erode the floor very easily. It'd be sort of an abrasive erosion. It wouldn't really be the chemical dissolution kind of erosion that we see. So I can't really give anything more elaborate than has to have done it.
Maybe a final point. So if you had to do this exact study,
Yeah.
very long time.
Yeah.
Might be possible to do, but do you anticipate patients to see lots of natural variation?
Yeah.
In terms of the process that you're seeing?
Yeah. So I discussed this with Rice because a lot of studies, mine included, and a lot of studies, they're always on one drill hole that goes through vertically, right? And we do everything on that. Do everything on that, and we extrapolate kilometers and kilometers and kilometers, and it's very frustrating. When you're not here in South Africa, being able to go and see these things and sample things, then we have to sort of make do with what we've got. I would expect things to change, and I would expect things to change with sort of the nature of the interaction it has with the floor rock. If it's a less fusible floor rock, we might see less, I would assume we have less amoeboidal chromites. We have less sort of weird inclusions, I'd presume so. But I would assume things would change along strike. And we know they do, the number of chromites change. That would need to be explained as well. Is it multiple replenishments meant for each one? I think it's probably the easier way to do it.
Have you considered the temperature relations involved in producing an andesite as a rest site part of the melting?
So removing, it gets very hard to melt once it's purely just plagioclase. Actually, melting the orthoproxene out from the footwall actually is quite achievable with a B1 melt. If it's maybe like the relative volume of it is maybe like 100 to 1, something like this. But the actual thickness of that anorthosite in our particular case is actually very small. So melting it thermally has actually been quite easy. So
this is the rest site, and what is the temperature of the material before?
So in the models, the footwall temperature was set to around 800 degrees, and the replenishing melts was set at the sort of the liquidus temperature, which was around 1,250 to 1,300 for variable mixtures of B1 and B2.
If it's that cold, 800, then that means that it's already solidified brittle stuff. It's going to be much older than the melt's coming in, right?
Well, because I assume the football norite is fully solidified. Because, yeah, so it has to have been somewhat pretty much close to being fully solidified. In the age between the anorthosite and the material overlying it. I mean, I'm not sure how much I believe any of the geochronology from these horizons.
Really?
Yes.
Oh, you don't believe geochronology? Maybe you should take some of our honors courses.
I think knowing what the ages truly represent is somewhat challenging in late intrusion.
I'm just more concerned with the model of heating it up. I mean, you've got 800. What is the temperature being coming out?
Around 1,300 or so.
How much?
1,300 or so.
1,300. And that's to produce a melt at what temperature?
The football melt.
What is the, you're extracting a melt?
Yes.
Producing rest melt.
Yes.
What is the temperature of that melt extracted?
Oh, I wouldn't know the number exactly off my heart now.
It's not less than 1,300.
Yes.
Higher than 800.
Yes.
I don't see what kind of melt that's going to be. If that melt is anything like a norite or salt, you're going to need 1,200. You're going to need huge, something much larger than that. So I'm not sure if this model fits together with the temperature relations. Also, we're worried about the volume. We're producing a tiny oxide layer by intruding something. I don't know what the volume is. It's big, I suppose.
Yeah.
And you wind up with a thin layer on the north side that has already yielded some melt. I presume that you're going to want that melt to blend in with whatever's being.
Oh, by some mechanism, yeah, sure. Sure, yeah, sure.
Yeah. I wonder what effect that would have. Probably not.
No, thank you, I appreciate it.
Do you really need melting? Maybe you can do this with this solution.
Again, that'll be something that would be very hard to actually find evidence for one or the other. I think there's a lot of circumstantial evidence that there was trap melt in this horizon. I think the abrupt contact and the observations we made at the contact between the football in the anorthosite and the norite are quite compelling, but actually finding conclusive evidence for dissolution versus just thermal melting, I think that's a very difficult thing to find. Because you did similar models that showed similar things, right? With the UC.
Yeah.
So
when we dissolve, we are not melt. We dissolve 15 liters and some hours, but we do superheat. Melting is really problematic. I agree with you. Solution is not.
I'm a geophysicist, for example.
Always trying to say
yeah.
You showed one experimental example that I'm assuming is an analogous experiment. You're just using it as an analogy.
Oh yeah, absolutely.
So how much experimental hydrology or whatever has been done on any of these models? Are we seeing anything like this?
No.
Or are we just
Not really.
nothing
No.
has been done?
No, I think that's honestly a bit of a frontier to do some more of this analogous kind of modeling, like really simple stuff, and just see how the coarse crystals form and what traps beneath them, how do they grow up at the top. I think there's a lot that could be done there, and a lot can be taken from analogies from extrapolating to these intrusions. But a lot of those studies are in the 80s. I had to really go looking for them.
This doesn't seem to be something that's being done about.
No.
The other question I had was about the 3D imaging.
Oh yeah.
You're working with thin sections. Have you started looking at any of the 3D methods, for example, the neutron tomography and others?
Yeah. So
they
there's
really have pretty good resolution.
yeah. And there's a lot of tomography done by Belinda Godell at CSIRO at the moment. Just getting the right samples. So I guess part of being here would be to get some of those samples and think about how we can use those sorts of tools. Because you're right, we're seeing thin slices of rock of something that's so incredibly large that actually going from 3D would be entirely optimal. So I fully agree. We work with what we got, and if we can get more samples and disprove half of that, fine.
It's just to scan them, or you have the neutron or CT scan?
Yeah, we have the CT and the high resolution scans to do. Yeah.
I know there's a mention inclusions which have some high minerals.
Yeah.
From a few reasons, Merensky, I remember there was a
Yeah.
huge lot of crystals. Then I have some increase which often transition to alcohol and other samples.
Yeah.
So can you say something about how this was the melt extracted from what was became a lot of
Yeah.
and how this was melt?
Yeah. Oh,
Anything about
yeah.
role of water and fluids in this?
Yeah, I could really only speculate on how much water there'd actually be in that. There's, as I said, at that horizon, there's a bit of a peak of phlogopite, nothing crazy to write home about, so it can't be an incredible amount of water, but clearly enough to locally crystallize very small amounts of argosite within the chromite. Because we don't see amphiboles really outside of the chromatites at all. So they can't truly be representative of what was crystallizing at the time. So small localized bursts of small amounts of water, fine. Yeah, can't think it's a lot. Yeah.
Any other questions?
For your section, which items did you guys use?
Oh, that's just from other studies. It's not necessarily from ours. So that's from like strontium isotope studies that show that there's this chemical break at that Merensky transition. Not from us. I think no more strontium isotopes I need to do.
Any other questions? Okay. Thank you very much. We appreciate your talk, and let's see how your
See how quickly it changes. Yeah, sure.